It's my pleasure to invite Professor Saket Saurabh from the Institute of Mathematical Sciences in Chennai today. So Saket received his PhD in computer science from the Institute of Mathematical Sciences in 2008. He spent 2 years as a PDF at University of Bergen, Norway. He's now a professor at IMSc and also at the Department of Informatics at University of Bergen. Saket's primary interests are in graph algorithms, parameterized algorithms, and complexity. Saket is a recipient of many awards. He is a SwarnaJayanti Fellow in Mathematical Sciences, which he received in 2018. He is now a Fellow of the Indian Academy of Sciences, the Academia Europaea, and the European Association for Theoretical Computer Science. He received the inaugural ACM India Early Career Researcher Award in 2020. And recently he was awarded the Shanti Swarup Bhatnagar Prize for Science and Technology, the highest award in sciences in India. He is also a recipient of an ERC starting grant and an ERC Consolidator Grants in parameterized algorithm. Saket is, of course, very well known to everybody in CMI, and so it's my pleasure to invite him. Today he'll be talking about graph isomorphism on structured inputs. Saket, the floor is yours. Saket, you can start.
I'm not sure if you could hear you.
Saket, can you hear me? Okay.
There's a problem in the connectivity. Just a minute. If you can hold on.
Okay, sure. No problem. Hi, Sushmita.
Hi, how are you?
Good. How are you?
Just sort of getting by, I guess, but not much to complain about.
Correct.
Okay. Sorry, I mean, as much as I tried, something had to happen at the last minute. So
I thought you suddenly had an algorithm to solve the graph isomorphism problem.
No, I didn't.
And a way to write.
Yeah. So can I start?
Yeah, sure, please.
Okay.
Yeah.
So thanks a lot for inviting me. It's a great pleasure for me to come and talk at our own school. And so today I will talk a little bit about graph isomorphism on structured inputs. So let me straight away go and define what problem we are going to talk about. So in the graph isomorphism problem, you are given two graphs G1 and G2, and we are to check if they're isomorphic. So in this picture, we are given two graphs, and we want to know whether they're isomorphic or not. So here's one isomorphism, which is basically labeling the vertices of these graphs such that there's a bijection between vertices, and there's an edge between two vertices if and only if there's an edge in the other graph. So if you look at this example and look at A is mapped to A, X is mapped to X, they look very different graphs, but with respect to this function, they are bijected. There is a bijection between vertices, and there's an edge in one graph if and only if there's an edge in the image of those two graphs. So this is a very classical graph isomorphism problem. And what is known about this is the following. So in 2016, Babai gave an amazing algorithm for this problem, which runs in quasi-polynomial time. So basically n to the power polylog in time. And in this talk, I'm not going to talk about this result. So that's a first, but we will come back to this result and say how this result has impacted this whole area on structured inputs also, and the kind of algorithms people have been able to design leveraging this algorithm at the end. Okay, but at least there's something which this result tells us is that graph isomorphism may not be NP complete. So this is one information that we can definitely derive from this new result, that it may not be NP complete. Okay. So in this talk, I'm going to talk about graph isomorphism has been studied on graph classes for years and ages. So one reason is that we believe that, we can get some ideas from this tractable instances of graph isomorphism as much as possible, and maybe it can help in the general case. So this is a naive motivation, but maybe the actual motivation is to provide a better understanding of various methods on these classes. So I would say that is a much more real motivation than saying that it could help in the general case, but you may never know. And so polynomial time solvable cases of problems on graph classes has been done from early 70s. So on trees, Kohli gave an algorithm in 1957, then planar graphs, interval graphs, permutation graph, bounded genus graph, bounded degree graph, graphs with bounded eigenvalue multiplicity, bounded tree width graphs, graph excluding a fixed minor, graph excluding a fixed topological minor. So there's a history of these results that has happened over the years in last 40, 50 years. Okay, so I'm going to talk about some of these polynomial time solvable cases and the kind of contributions we have been able to make in this area. So let's look at the simple algorithm for graph isomorphism on trees. So you are given two trees and you want to know whether they're isomorphic or not. So what you do is that you root the first graph on some R1 and you guess its image in the other tree R2. And then you run a bottom-up dynamic programming with the following table. So what are we going to store? So for every vertex in VG1 and every vertex in VG2, TUV is the answer to the following question. Is the subtree rooted at U isomorphic to subtree rooted at V? Okay. And since we are doing bottom-up dynamic programming, you already have stored information about the children's and their corresponding isomorphism or not. Then what does this problem becomes? This problem basically becomes that, and of course, if you look at the root, that is an answer. So basically the computation of one step boils down to a matching problem. Why? Because all you want to know that, okay, you know that U has following children, V has following children, and now you want to know whether the subtrees corresponding to them has some sort of isomorphism or not, which basically means that I pick up one here, and so I can make a matching problem as follows. I make a subtrees here, and one node for subtrees here, and now I have stored the information whether this subtree is isomorphic to this or not. Then I put an edge. So now basically you are looking now for a perfect matching in this graph, right? If there's a perfect matching, then every child is isomorphic to some other children of this. And if there is such a matching, then you know that the subtree rooted at U and subtree TUV are isomorphic to each other. So we can do this one step in a matching way. But if you do this naive way, it will take you some n to the power 4.5, but there are much faster algorithm known. And there are algorithms which can take linear time, in fact, on isomorphism of trees. But this is a very simple algorithm for doing graph isomorphism on trees, just to get you feel for the kind of things we might be doing later. Okay. So there's also we can do planar graph isomorphism. So the way planar graph isomorphism works is follow. If you're given a graph G, in linear time, you can compute its decomposition into 3 connected components. And the property is that this decomposition is isomorphism invariant. So if you take two graphs that they are isomorphic, you will compute a decomposition which are isomorphic to each other. So basically decompositions are like trees. And what more do we know about? That any three connected planar graph has unique planar embedding, meaning you know what planar graphs are. They're basically, those are those graphs for which we can put the vertices in plane and draw edges between two vertices in a way that they never cross. And what do you mean by unique planar embedding? So however you do, if you think for a minute, you take a planar graph, there could be various ways of drawing a planar graph in the plane graph in the plane. Okay, but if the planar graph is 3 connected, then there's a unique way of doing it. And what do you mean by 3 connected? Basically, you cannot separate this planar graph by deleting, say, at most 2 vertices. Means you cannot disconnect. So the graph where you need at least 3 vertices to delete, so the graph becomes disconnected, are 3 connected planar graphs. So you can define K connected and so on and so forth. So you combine these two, so the way the isomorphism algorithm will work is that it will compute this decomposition into the pieces, 3 connected pieces, and for them, compute this embedding and then compare them. Okay, so this is how planar graph isomorphism works. Okay, but in this talk, we will worry about tree-like graphs. Okay, and what I mean by tree-like graphs, so this is tree, okay, and this is tree-like graphs. So the best way to remember tree-like graphs or trees are, in some sense, it is more or less equivalent definition, is that I'm going to call a graph tree if give me any subset of vertices, I can find you one vertex to delete and that graph becomes disconnected. So in tree-like graphs, I will say maybe this I will replace the word one with some number 5, 7, k. Is that you give me any subgraph, I can find some k vertices. If I delete those, the graph becomes disconnected. Okay. So for example, if you look at this example, then you give me any subgraph of this graph, I can give you 2 vertices so that if you can delete, the graph becomes disconnected. So the usual definition of tree width is very cumbersome to keep in the head. But this alternate view with respect to separators is almost equivalent. Like, I mean, they are just constant factor approximate equivalent. So you can define a notion of k separable graph is basically a graph is k separable. If I give you any subgraph of that graph, you should be able to find k vertices to disconnect it, right? So basically, we will come back to the precise definition of tree width, but this is something to keep in head. And so if it becomes bit fat, you need k vertices to disconnect pieces of graph, then you call tree-like graphs whose width is at most k. And so this is like Chandelier trees. So why it is tree width? So I had an opportunity to talk to Seymour and just asked him, and he said, well, haven't you seen a tree? The width is like, if you want to cut the tree, so as you go up, you can disconnect the tree by like everything is lesser than the width of the tree or the width. Okay, so this is why it seems like for fun day they kept it. So this is why in the tree width graph, like you can separate the graph with like some whatever the maximum number of width or number of vertices you need to separate any piece is what is the tree width of the graph. So this is a very good thing to keep in the head, is that from where the word tree width comes. Okay, so now let me define it formally. So what is a tree decomposition and tree width? Okay, so tree decomposition is basically tree of bags. Okay, so now look at the graph on the top here. And basically what I have done here is I have decomposed this graph as trees, but where every vertex is not a single vertex anymore, but a subset of vertex of my graph or a bag. Okay, for example, this 4 vertices has become a bag now. Other set of vertices has become a bag now, so on and so forth. Okay, and this tree structure has some property. And what is the first property? Is that given a graph, every vertex of that graph should be mapped to some bag on this in this tree decomposition. So basically, it's tree of bags. Every vertex should be part of some bag. And the second property is for every edge, there is a bag that contains both the endpoint of that vertex. And finally, look at a vertex. A vertex can be mapped to several bags. It is not a partition of the vertex set. So vertex can be mapped to several bags, but the bags in which a vertex appears must be a connected subtree. So for example, look at the vertex S. It appears here, it appears in this bag, in this bag, in this bag, and this bag. And if I look at the set of bags which appears in this, they all are connected. Okay, so these are the 3 properties that we expect from a tree width or tree decomposition of a graph. So what is a tree decomposition of graph? Given a graph, we make bag of trees. So we have a tree where every vertex is associated a subset of vertex called bag, and they satisfy 3 properties. Every vertex is in some bag. For every edge, there is some bag, and bags containing a particular vertex are connected. Okay, so this is the property of, this is the definition of tree width. And what is width of a decomposition? It's basically maximum bag size minus 1. And this -1 is historically done to show the tree has tree width 1, but it doesn't matter. Okay, so this is a very formal definition of tree decomposition, but algorithmically it is just equivalent that I can separate the piece of my subgraph by a small number of vertices, and or this is a recursive definition or separable definition, which is equivalent and which is used way more than this definition. This is largely used to do dynamic programming algorithms or some such things, which I will show as we go further. Okay, and the tree width of graph is a minimum width of a tree decomposition. So given a graph, you can make several decomposition. The one where the bag size is minimized corresponds to the minimum width of a tree decomposition or the tree width of the graph. Okay, and there's a very beautiful property that every edge of a decomposition, it's a good, like you look at any edge of this tree, okay, and if you look at the intersection of this bag and delete the vertices, then that will decompose the graph into two pieces. Okay, one containing the vertices here, other containing all the vertices here. So every edge of this bag basically witnesses a separator or a separation of my graph. Okay, so now let's go back to a parameterized complexity of graph isomorphism. So a basic question is graph isomorphism solvable on graphs of low tree width? Okay, there are two possible answers. One is algorithm that works in polynomial time for every fixed k, example n to the power big O of k. And the second possible answer, that algorithm that works in linear time or quadratic time or cubic time for every fixed k, example an algorithm of the form f of k poly in n. Okay, so the first kind of algorithm in parameterized.
1 minute, Saket, 1 minute. You're mute. It's suddenly gone to mute.
Oh, sorry. Okay.
Yeah.
Oh, so so as I was saying that, so given a number k, I want to check whether two graphs of tree width k are they isomorphic or not. So I could have several algorithms, right? One of the form n to the power big O of k, other f of k poly in n. Now the first kind of algorithm are called XP because they're polynomial time for every fixed k. So if you're looking for tree with 3, it's like some n to the power big O of 1 algorithm, right? So in that sense, it generalizes the algorithm for trees. But the other answer could be that we have an algorithm with running time f of k times n square. So it's a quadratic algorithm for every constant. Okay, so these are the two kinds of answer we can expect for this problem. And already by 1990, Bödlander had showed an algorithm that graph isomorphism and canonization can be solved in time n to the power k plus some 4.5 on graphs of tree with k, right? So we already had a result from 1990 whether two graphs of tree with k are isomorphic or not of the form XP. And what was not known whether we have an algorithm with running time f of k poly in n or whether it is FPT or not. So what we showed in 2014 is that in fact, we can get an algorithm with running time 2 to the power big O of k to the power 5 log k n to the power 5. So we give n to the power 5 algorithm for every fixed k. So for trees, we give n to the power another n to the power 5 algorithm in some sense, and so on and so forth. So in this talk, I'm going to give you a glimpses of this result. So as KV wanted me to give a technical talk, so I will give you almost full details of this talk in this talk of this result. So I think there is
a question. 1 minute in the chat. I'll just ask you because it might be useful. Are there algorithms for good bag decomposition?
Yes, I will tell you now.
Okay, good.
Like it will be a self-contained algorithm in a minute. Okay, and then we will make an algorithm of this nature. Okay, so in fact, apart from bounded multiplicity of eigenvalues, one of very few FPT results in graph isomorphism. So already in these 80s, people had designed this algorithm for like, so it was actually an FPT algorithm parameterized by a number of like distinct eigenvalues. So yeah, so no, not multiplicity of eigenvalues. So like how many copies of eigenvalues are there? Parameterized by that, people had already designed an FPT algorithm. But apart from that, all other algorithms, like by bounded degree on all this, are of this form, which we will talk about later towards the end. But in the meat of my next 25 to 30 minutes, I will talk about this result. Okay, and on that way, I will also give you an algorithm, as one of the speaker asked, is there an algorithm for good back decomposition? The answer is yes, and I will give you one such algorithm. Okay, so comparing tree decomposition. So suppose G1 and G2 are given together with tree decomposition T1 and T2. And suppose further that you want an isomorphism that also preserves the decomposition, right? So given a graph, you can compute several decomposition, but suppose I give you two graphs and I give you their decomposition also and say, hey, give me an algorithm that preserves the decomposition also. Okay, then it is easy to test whether isomorphism of pair G1 T1 and G2 T2. How? Again, just like trees, okay, you guess matching roots of tree decomposition. Okay, you do perform bottom-up dynamic programming and computing isomorphic subtree with labeled vertices in the top backs. What I mean by that, so you have one vertex which has some subset of vertices and some subset of vertices. You know that this vertex is going to be mapped with this vertex. And now you say, look, who is going to be matched from here? Who is going to match to this vertex? Who is going to match to this vertex? So basically you have guessed a function or a permutation from the vertices of this bag to vertices of this bag, and you are asking, is there a way to extend this bijection to the subtree rooted at this? So whatever we did before for a tree with a single vertex, now we generalize this to this decomposition of bag by for every bag going over every permutation and trying to put in the DP table, is there an isomorphism that preserves this labeling of vertices of this bag and this labeling of vertices of this bag? And if there is such a labeling, I put it one. And we can do this dynamic programming bottom up as we had done for the trees. Okay, but what is the point here? We are trying to preserve that not only graphs are isomorphic, even the decomposition which is given, the two trees which you gave me are also isomorphic to each other. Okay. Thus, in some sense, we look for an isomorphic invariant way to compute a near optimal tree decomposition. Okay, but the major problem is how to compute an isomorphism invariant tree decomposition of the graph. Like, how can you compute a decomposition of the graph which is isomorphism invariant? I will define what I mean by isomorphism invariant in a minute. Okay. So, like, what I mean by isomorphism invariant, basically, whenever you talk about isomorphism, you cannot make any arbitrary choice. You have to have an algorithm. Like, there should be a unique way of doing something. Like, so if I apply the same operation to the both graphs, then I obtain the similar result. But I can't say, oh, pick up an arbitrary vertex and do this, pick up an arbitrary edge or do this. These kind of operations are not allowed because that is not an isomorphism invariant way of doing things. You will see some of these things coming up in the next few slides. Okay. Note that decomposition can have width bounded by some f of k. It does not have to be bounded by k. You could compute any isomorphism invariant tree decomposition of any width which is function of k, and that could be useful for our purpose. So we do not actually achieve this goal, but almost something very close to these kind of things that we achieve. And I will give a pointer to that in a minute. Okay. So what are we going to do it? So what we are going to do is that we are going to compute an isomorphism invariant family of candidate bags. Okay. So notice that whenever we are decomposing into these bags of the trees, like our basic objects are bags. So I'm saying that if I can given a graph G, I can compute a canonical way, some bags, and say, hey, here is the following property. Like, given a graph this, there's a unique way to compute this bags. And another property is that also you can actually compute a tree decomposition of width f of k using these bags. Okay, so I'm going to provide you an algorithm which is going to do these two things. One, given a graph G, it is going to give you an canonical way, like a unique way to make these bags. And the additional property of these bags will be that you can actually compute a tree decomposition of width f of k using only these bags. Okay, so every bag of t is in these bags, and note that there can be increase in width. So even if the tree width is k, my bag size could be poly k or f of k. I don't care. Okay,
So the first, Saket, just one question. So the first G going to BG. So you're saying whether I take G or an isomorphic copy of G, the BG, the B that I will get should be the same.
Exactly.
Okay.
That's exactly what it is. You're right. So given any two graphs which are isomorphic, B of those is going to be same.
Okay.
So you're right. This is exactly what I mean by isomorphism invariant. So if you give me two graphs and compute the function on that, the output will be the same.
Okay. Okay, thanks.
Yeah. And the second property I need is that the number of bags are not too many. They are only a function of K and some polynomial. Okay. And given such a family of bags, it is not hard to perform canonization, in fact. Okay. And it was already known from long time. So what we do is that given this set of bags, we compute like lexicographically smallest construction that we can get from BG. And since this is unique, or this is isomorphism invariant, then you can just compute this construction term and just compare it. But if that is not important. I mean, those are like something which is like hardware. So how did Bodlander did? So he said, hey, look, if it is going to be given G and BG, let's take all sets of size K+1. I mean, definitely you're going to capture all the property, right? Like if tree width is K, there is no bag of size more than K+1. So let's take all vertices of size K+1, right? So definitely you are going to capture, and this is isomorphism invariant because look, I am not making any choice. Given a G, take all subsets of size K. So given two graphs which are isomorphic, you will get the same subset. And then they performed this, okay? In 2014, Otaki, yes, Vamadi, not all the bags need to participate in the bag decomposition. You're right. It's just that it should contain a subset of bags which can give you this decomposition. So you can produce much more thing, but it should just have the property that it has some subset of bags which can give you odd tree decomposition. It need not all of them could be used, because look at here, like n choose K, but in the tree decomposition, as we will see, all you need is just n bags. So yeah, far too many of them. But all you care is that there are enough of them. From there, you can compute odd tree decomposition. Okay.
Okay.
Good. Okay. So there's something called Weisfire-Lemon trimming of K+3 dimension can also do this job. That was by Otachi and Swarup in 2014. I don't know too much about Weisfire-Lemon to tell you what it is, but it also does this job. But this also will produce n choose K. So this did not do the job which we wanted. Okay. So now we are going to focus on finding an appropriate family of candidate bags. So this is what I'm going to show to you, how to find appropriate family of these candidate bags. Okay. And what is our main idea is to take an existing approximation algorithm for tree width and make it almost isomorphism invariant. And now I will answer the question of so I will tell you how that algorithm works and then show you how to avoid arbitrary choices in that algorithm with some specific choices, and that works. Okay. So this algorithm originates in graph minor 13, and this is called Robertson and Seymour approximation. So what does it do? It takes a graph G and integer K. It concludes that tree width of G is strictly greater than K, or it produces a tree decomposition of G of width at most 4K plus 4. Okay. And this algorithm is actually there in Kleinberg-Rentardo's book also. So this is, okay. And the running time of this algorithm is 8 power K, K square dot n square. Okay. And by now, this is basic methodology for almost all algorithms for computing tree-like structural decomposition. So this is like the basic algorithm that we all start with, and from there, try to build anything based on our need. So I think this is basic enough that I thought as a modern algorithmic techniques, maybe you would like to know. So our plan for now is to give you slightly worse running time and prove you a bound of 4K plus 4. Okay. So decomposition will be constructed recursively in a top-down manner. So what are we going to do is following. So we are going to solve more general problem. So input is graph H, a subset S of V of H. And invariant, I'm going to maintain that this set S has always size at most 3k plus 3. Okay. Now, our goal is to certify that tree width of H is strictly greater than or equal to k, or compute a tree decomposition of H of width at most 4k plus 4, and with the extra property that S is contained in the top bag. Okay. So, and why are we doing this? I'll show you why are we doing this. So intuition is that at any point of time, recursively, H is going to be an induced subgraph of G, and this S is a small interface between H and the rest of the graph. So here, this is going to be like H, and this is set of vertices with neighborhood in the other side of the graph, which is bounded by small number, right? So this interface is going to act like a S. So this is why we are doing this induction on much more general thing, because inductively we will have a induced graph with small boundary looking into the other side of the graph. And because it is an interface, you like to join them there. And that is why we are demanding that you give me a tree decomposition where every vertex on the interface is in the top bag. Okay, so that is an intuition of defining this more general problem. Okay, just to take care of what are you going to get in the recursive step. Okay, so here is a very beautiful property or beautiful definition called balance separator. So what is balance separator? So set X is a half balance separator of S. If you look at a connected component of H minus X, it contains at most half the vertices of S. So imagine that these are the green vertices are your X. Okay, this green vertices is S and this yellow vertex is X. Now I'm going to call X is a balance separator, a half balance separator, if every connected component contain at most half the vertex of S, right? Now, if tree width of G is K, then every set S admits a half balance separator of size at most K plus 1. Okay. Okay. So there are several proofs. I will tell you one proof, but one proof is very easy. Look at your tree decomposition and root it at some place. Okay. You ask yourself a question. Either this vertex, either this bag of K plus 1 size does the job. Why it is not doing the job? Because some children contains more vertex than half, strictly more vertex than half. Then you move the token to the child. Now you notice that, and you ask the same question, is this bag does the job? But notice that if this bag does not do the job, you can move the token again to the child. And since the child below contains strictly more than half vertices, everything otherwise contains strictly less than half. So you can move the token down, down, down. And because this is a finite steps, you will eventually reach a set such that every component contains at most half the balance separator. So this is one proof. The other proof, which is more easier, is that you take a tree decomposition T of width at most K, and now you orient every edge of T to the side that contains more vertices of S. So you take this edge, if it contains strictly more vertices of S, then if you delete this edge, you get subset of vertices in this bag, subset of vertices in this side of the tree. You see which has more vertex of S. You just orient that edge. Okay. So there is a bag of the tree decomposition that has out degree 0. Okay. And this bag has the required property. So you can show this. So this is this is simple, but this is the property of tree decomposition that people use to design all kinds of algorithms. So this will give you very interesting divide and conquer algorithm, very interesting dynamic programming algorithm, and all kinds of things. Okay. Okay, so what is a balance separation? So it's a partition AXB of V of X is called 2 by 3 balance separation S. If, first of all, there is no edge. So this is say A, and this is say B, and this is my X. So there is no edge from here to here. There is no edge from here. So if I delete X, right, then there is no edge between A, like there is no edge from A to B. And it is called 2 by 3 balance separator for S if the number of vertex of S in the A side and the number of vertex in the B side is upper bounded by 2/3 of S. Okay, so you are doing at least both sides contains significant fraction of S. It's not that one side contains less, other side contains more. It's not skewed. It's like more or less you're getting something in both sides. Okay. So here's the lemma which says if the tree width G is at most K, every set S admits a 2 by 3 balance separation of size at most K plus 1. Okay. Okay. Why? So here's a simple proof. You take X to be a half balance separator of S, okay? Because for every set S, there's a half balance separator. So you take that. Now group components of H minus X into A and B. And this is always possible to show that you can group these components in a way that A contains at most 1/3 of, like at most 2/3 of S. Like you just look at the heaviest bag. You know that either it contains, everybody contains at most half of S. So you just check the first bag. Does it contains strictly less than 1/3 or strictly more than 1/3? If it contains strictly more than 1/3, the heaviest component, then you know that it contains at most half. So you take that into one piece, every other component into the other piece, you have at most 2/3 in both sides. Otherwise, any component contains at most 1/3 of S. Now you start with, you sort the components based on the number of vertices it contains from in the decreasing order. And the first time you go strictly more than 1/3, you stop. You know that before that, everybody was 1/3. So you added at most 1/3 when you went this. So you have got 2/3 and the remaining guy is going to contain another 1/3, at least 1/3. So this is how you can do balance. And this is very important properties of tree decomposition. Okay. So now we are in this case. So we are going to maintain invariant that cardinality of S is at most 3k plus 3, and we are given this. Okay. So first of all, we do something very simple. We add arbitrary vertices to S so that cardinality of S becomes exactly equal to 3k plus 4. If it is not, then you know the graph itself is small. You output that as your bag and you are done. Okay. And now from lemma 2, I know there's a 2/3 balance separator A, X, B of this S. So I have X. I know this X is large enough that I can split it 2/3. What is the meaning of this? So if you intersect with S, there's a partition SA, SX, and SB of S such that how many vertices they contain? SA and SB contains 2/3 of S. So S was 3k plus 4. Then if you do this maths, you're going to get it 2k plus 2. That's great, because now what I know, minimum vertex cut between SA and SB in H minus SX had side at most k plus 1 minus SX. So now I know something very interesting, that both sides contains SA, and there is a subset of S which can be disconnected by at most k plus 1 minus S of X vertices, or at most k plus 1 vertices. So this is a property of, now because I know such a good split exists, but how am I going to find it, right? I know that I can split S by this property, but now what I'm going to do is that I'm going to iterate all possible SA, SX, and SB and check. Okay. So there are at most 3 to the power 3k plus 4, right? What I want. So I want to do algorithm, right? So I have to find, I know that there exists a balance separation, but how do I find such a balance separator? So to do that, I said, okay, fine. Let me try to do the following. Let me guess SA, let me guess SB, and let me guess SX, right? SX I will delete. SA and SB I will apply min cut, okay, by doing some k round of fold recursion and see if I can separate them. If I have separated them, then I know that I have found all such separation, and then I will do recursively, okay? And if I don't, then I have showed to you that tree width of this H is strictly greater than k. Okay, otherwise you can produce Y, the min cut. Okay, and the moment you have min cut, I'm going to recurse by taking this as my top bag. But how many? What is the size of this bag? Well, it is like S union Y. So Z is so the top bag will be 3k plus 4 plus k plus 1, which is 4k plus 5, which is fine. Okay. But now when I do recursively, I have to ensure that when I do recursively here, the size of S is not more than 3k plus something, because that is what the inductive hypothesis I have. So let's check that out. So I'm going to apply recursion on graph induced on A union SX union Y. This is one. Other is going to be SB, SX, this. This is for this border, and this is for this border. Now I'm going to call inductively on these two graphs. So, but I have to make sure that SA is not larger than some 3k plus something that I started with as an invariant, let's check that out. So what is SA? We know that size of SA is at most 2k plus 2, and this Sx plus y is at most k plus 1 because they are separator. So this is 3k plus 3, and we can simply do for SV, and we are done. Okay, great. So now we can recursively on instance on this, and finally, once you get a decomposition from here, you can just glue as a child. So you have taken this as your one bag, which is root bag. Now you just make this as root bag, like look at this root bag, make a tree from this, map it here, make a tree for this, map it here, and then you have got a tree decomposition for the everything. So recursively, you can glue this to get a tree decomposition as the children of Z. So this is basically, this is how you get a constant factor approximation for tree decomposition. Okay, so what is the running time? At every call of the recursive procedure, S was augmented by at least one vertex. Okay, so algorithm is going to halt and produce at most some n bags at any point of time. Computation for each bag, there are at most 3 to the power 3k plus 4 runs of max flow algorithm. And so this can be done in k square n time. So if you do the computation, this is what you're going to get at your running time.
Just one question.
Yes.
You have not told, sorry, you have not told how you got A and B.
Oh, how I got A and B?
Yeah.
I actually, I told you how to get this A and B. It basically, you just group the components.
Oh, I see. Okay.
Just group the components based on where their neighbors are. Or if, like, to be honest, it even does not matter. You can recursively do on every connected component. Look at a connected component. You can call every connected component with its boundary. So look at Z. Okay. So here is my Z. Delete Z. Now look at any connected component. Now you know that this connected component here sees at most 3k plus 4 vertices. So you can recursively call your problem on each of the connected component with this.
Okay.
That also will make progress. And we will do that for isomorphism problem. Okay. So what was the crucial trick? To recurse, we want to break the graph using a small separator. Okay. Adding any separator can dangerously inflate the size of the adhesion or the top bag which we made, where we did, right? So we found this set S and we separate it and we make a bag which consists of S union Z. And that is why we had 4k plus 5 size bag, right? So it is important that you find this Z in an appropriate fashion. Otherwise, when you do recursively, you cannot guarantee that every component has at most some 3k plus 4 vertices in the S side, right? So it is important that you separate this in a balanced way so that the piece of S that any component sees is not more than 2/3 of S. Okay. Now, so we break the adhesion in a balanced way to compensate for the new separator. Okay. Now, instead of left, right, which we did, we could have recursed on connected components of H minus Z, right? So delete Z and you recurse this on every connected component and you would have got the same set of results. So the closed neighborhood of the component, so here is the Z, as I said, look at a connected component, the role of S will be look at the neighbor here, right? This is what the role of S will be, and you recursively compute on this. Okay. So there's a problem with isomorphism invariance. There are two problems. Step one, we said, look, why did we add vertices to S? Because if it is not large enough, I cannot guarantee that I can break it. So to break it, it is important that S is sufficiently large enough. And that is why we added arbitrary vertices so that the S becomes 3k plus 4. Okay. Now, if you want to do this bags business in an isomorphism way, you cannot say add any vertex, because if you take two isomorphic graph and if you add one vertex here, but if you add non-isomorphic vertex in the other bag, it will just spoil the set of bags that you can get. Break S using an arbitrary balance separator. Again, arbitrary balance separator. This anything which is arbitrary must be avoided when we are talking about isomorphism. So what I'm going to talk you how we can modify this algorithm to circumvent both of these problems. So like what will be the right step to say add arbitrary vertices to replace something, take arbitrary balance separator, replace with something, and still say that we are making progress. Okay. So here are some simple observations. Okay. If vertices U and V can be connected by K plus vertex rejoin path, so you have U and V, and you have say K plus 1 vertex rejoin paths. Okay. Then I claim that every tree decomposition of width K will have a bag containing both of them. Okay. So which basically tells that if there are two vertices which has a high flow between them, then those two vertices must be in the same bag in tree decomposition. Why? Because imagine that U is somewhere and V is somewhere in some bag and some bag. Now look at the path between them. What you know that this is like, okay, this is like, it has a bag of say size K plus 1. Okay, so if you don't put them into this, then you know this bag and this bag intersection is going to be size at most K. But if I delete this K vertices, U and V get separated. So how can you separate U and V, which have K plus 1 vertex rejoin paths with subset of size K, right? So which basically means that, because as I told you, right, every edge on the tree decomposition, if you look at the intersection of these two bags, that separates vertices appearing here, vertices appearing here. So if there are two vertex U and V with very high flow, you are always guaranteed they are going to appear in the same bag. So this lets us to define the notion of what is called improved graph. So what is improved graph? So this we can do as a pre-processing. So if you add UV, you cannot increase tree width larger than K. So whatever tree width was before, tree width remains the same. Okay. So what we are going to do, we are going to do this operation exhaustively. Okay. And this is why I'm going to go call it improved graph. So what I do, given a graph G, if there exists a vertex UV with flow at least K plus 1, add an edge UV. Now this is not depending on any vertex. It's a property of graph, right? If two graph has any pair of vertex with this property, just do this exhaustively. I'm not telling do for this pair and don't do for this pair. So this is a what you call isomorphism invariant operation. Okay. So we can assume that the graph is improved. Okay. There is no vertex U and V, which is a flow of size K plus 1, and there is no edge between them. So then what is the meaning of this? So whenever there is a non-edge, there is a small cut, right? So if you have a two vertex U and V, which are non-adjacent, why did you not put an edge? Because the flow between them is strictly less than K, right? So you can disconnect U from V by cut of size K. By deleting K vertex, I can separate U from V. So non-edge implies small cut in this improved graph. So that's a property number 1. Okay. So now there's a notion of click separator. So what in a UV separator, X is called a click separator. If you look at U and V get separated, and the set of vertices which separates, that forms a click. Okay. And the great property of click separator are that they do not cross. What I mean by they do not cross, suppose here's a one click separator, here's another click separator. So now look at this click separator and look at the connected component. Okay. Now suppose this is A and this is B, and suppose it is A. Where will B lie? B has to entirely lie here or entirely lie here. Why? Because if B is in two pieces, then it's a click. So then there's an edge between them, right? So if you have a click separator, they cannot cross. Like, so if you delete, every click separator is in one piece or one part of the connected component. This is what I mean by click separators do not cross. Okay. So Laminar in 1993 showed that there's a well-defined decomposition along click separators. Okay. So what we are going to do is, this shape of this decomposition is not isomorphism invariant, but the bags or the set of vertices that you can get or the component you will get after deleting this are isomorphism invariant. So we will work on this subset of bags or this subset of vertices. Okay. And click separator free bags are called atoms. So what are we going to take? We are going to take our graph, first operation, make it improved by for every UV, if the flow is R, add this. Now compute all click separator, delete it, and get on the set of vertices which are called atoms. So now from now onwards, we are going to work on these atoms. And this is very important for us. Okay. So what we are going to do, we are going to compute candidates bags for each atom separately and then finally take the union of them. Okay. So we are going to make now second assumption. The graph does not have any click separator. Okay. And here's a very beautiful property of cuts. So if N of A and N of B are two minimum UV separators. So like U and V, you separate. So there is one blue cut and there is red cut, min cut. Then A intersection B is also a minimum UV separator. You look at the neighborhood of A union B is also a minimum UV separator. Okay, so this just follows from the submodularity that F A plus FB is greater than or equal to FA union B plus FA intersection B. So just by this, you can prove that they happen. But this has a very beautiful property is that now I can look at all min cut. Look at all min cut. So like there could be A1, A2. What I mean by this, neighborhood of A1 separates U from V. Neighborhood of open neighbor of A2 separates. Okay. Now you look at the intersection of AIs, right? This is also a separator and this is unique. Okay. You take union of AIs, this is also unique, right? So the intersection is called closest to you, union is called furthest to you, right? So because you look at any two cut, you say, hey, if they are not comparable, you can take the intersection, you will get something smaller in terms of reachability and show this object is unique. So given U and V, the cuts, like there's a notion of unique minimum separator that leaves inclusion bias minimal and maximal set of vertices reachable from you. So basically take intersection of AIs and take union of AIs and look at the borders. Okay. This is very important for us that given U and V, there's a notion of unique min cut. Okay. Step one. If S is small, I have to define, right? If you look at the previous approximation algorithm for tree decomposition, if it was a small, we arbitrarily added vertices, right? We can't do that. But now what are we going to do? If S is small, we are going to add arbitrary vertices to it so that it becomes large. This was the step one. Now we are going to have a different. So we are quantifying what small will mean. A small is mod S less than 10K. Then what I'm going to do for every UV in S, UV not in E of H, U not equal to V, let XU be the minimum UV separator closest to you, add all these things to this bag. Now, I'm going to do this for every pair of vertices which does not have an edge. Now notice, I know that for every pair which is non-edge, the size of this cuts is bounded by K. So two, you're not adding too many vertices to this bag. Okay, so this is how I'm going to get Z. Okay, now look at the statement. For every UV in S, UV not in edge, you do this. So there is nothing arbitrary. This is like whenever you are doing for all, let's do this. Okay. Okay. And since graph is improved, you know that every separator has size at most K. So you use this property. And why are you making progress? Because there is no click separator. So there will always be a non-edge here for you to cut and improve. Okay. Okay. So now notice that when we recursively try to, so what I'm going to do, we make it big. Okay. So if it is too small, we make it big. And for every connected component, we say, okay, go now recursively try to solve the problem for, look at Z, look at delete from Z, look at any component and look. Now, in the worst case, C can be looking everybody in Z, but still the neighborhood size is not more than order K cube. That's great. Okay. So that is what invariant will be, that at any point of time, the interface is nowhere more than order K cube. Okay. So that is the invariant we will try to maintain. So if I have a really small set, I do this. But if it is more than 10K, I will do separations. Okay. So do we always make progress? And why is there some non-edge within S? And the point is, we will always recurse on the instance of this form for some connected C. Okay. And how do we start in the beginning? Okay. How do we start in the beginning? In the beginning, so we will not make one, but for every non-edge, we will start in the beginning with S containing non-edge. So for every pair of vertices which does not have non-edge, we are going to compute this bags and then take their union. This is why we are getting n square overhead, because we don't know where to start. So let's start from everywhere, which is non-edge, and we know we can make progress. Okay, so in the beginning, this is what we call your individualizing two vertices. which is basically you're saying that these two non-vertices is going to be mapped to these two non-vertices in the other graph. Okay. Now, if S is large, you have to use S using a balance separator. Okay. Okay. So what we are going to do? So what we actually do, S is large, and where large is like roughly like KQ. For every set of size P and Q, P intersection Q is empty. Cardinality of P equal to K plus 2. We say if there exists a PQ separator of size at most K plus 1, then let's take a PQ separator which is closest to P and let's add to it. Okay. And we know because of balance separator lemma, there's at least one such pair because this is big. This green part is big. So you can always be able to separate. Because, so what I mean by this, okay, this is a big piece, right? So there always exists a balance separator for this, right? So if you take a balance separator, it is going to make some balance, some vertex here, some vertex here. So now this is also a separator of size K plus, like this is also a separator for this subset here and this subset here. So rather than trying all possible breakup, I have just taken P and Q of particular size, but you could also look at any possible breakup of this green guy into a small, and we know there is one such pair, so we will be happy. Okay. Now, what are we going to do? We're going to take all such things. So any subset of P and Q, if you can cut it with small, please take it. And we know that there is at least one PQ for which we will succeed. But there's a problem now. Okay. What is the problem? Is that
no, but the reason you take all of them, sorry, the reason you take all of them is again for maintaining invariance.
Maintaining isomorphism invariant.
Isomorphism.
But now imagine that for all subsets of size K plus 2, if you add this, this is exponential, right? Size of Z becomes K times this much. Now, this is bad because now if I do say, okay, take this big Z and look at a component and look at this neighbor. If I don't have a control, then what am I getting? If my invariant was that every time you call inductively, it shouldn't be more than say KQ, but now I have blown up the bag, what I'm doing then, okay? But then what we managed to prove is that this is a magical lemma, which says that for every connected component C of H minus G, neighborhood of C is at most cardinality of S. So whatever S you started with, every connected component had size at most S. So this has blown up. But every connected component still sees small number of vertices inside this big bag. So now you can do inductively. Okay. So this is a lemma which we were stuck for years.
But I'm a bit confused. Wasn't S large actually to begin with?
S was like K cube.
S was more
Suppose
than,
it was K cube. Now you did all these things and you made it Z. Now you look at any connected component outside this, right? If I do not say, and I want to say, let's recursively try to solve the problem here, right? So if I say that at any point of time, when I call inductively, the side of S, potential S, should never be more than KQ. So I have to ensure that this C sees very small number of vertices in this big bag Z. And that is not trivial to show. So in the first case, when it was 10K, I didn't care because anyway, I wanted to maintain invariant as KQ. But now my bag has become super big. So I have to make sure that every connected component sees small number of vertices inside. The proof of this lemma is not very big, but statement was a bit of mental trauma to believe that this statement is true. That you suddenly added lots of min cuts and you expect that now you take any connected component from outside. It is amount of vertices which it sees inside is upper bounded of what it was seeing before. Okay. So how we do about this? Let me give you one line argument for this. So we start with this and each time we add one by one separator and see how the component boundary looks like. Okay. So look at in the beginning, every component of H minus S has neighborhood only contained inside S. Nothing changed. But now I add one separator to my Z. Now look at any connected component. Okay. So any component is here. So in the beginning, this was a component. This was my component. Now when I added this I have got smaller size. Now what we are able to map is that, well, this size, so I know that in the beginning, I have a component C. Now, when you delete another separator, you are going to get C prime, which is going to see something inside and something from outside, right? Because imagine that I deleted first, I have got component. Now I delete another set of vertices. What I'm going to get is components are getting smaller, 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 smaller. So what we are able to show that, look at the old component, which had some boundary. Now we are able to give a map for a smaller component to the boundary of the bigger component that it comes from. And because bigger component had mod S upper bounded, we are able to maintain this invariant. So it is inductively done. So we need to make some border replacement argument. So let me just tell you that it's really not a long proof. It starts from here, and with big picture, it just ends here. So it is really a half a page proof. So it's not that I'm cheating anything, but trying to prove in a talk is like hazardous. It's like with so many symbols and min cuts going around that, but believe me, it's true. So this is a very good take home message, is that if you take a set S and you add lots of cuts to min cuts to it, and then you look component outside, it's what you call, its boundary does not change much. And that is a very important property to apply invariance, induction, or recursive algorithm. Okay, so here's a summary of my algorithm. So if mod S is less than 10K, we add minimum cut for every non-edge, we make bag size order KQ, we blow up, and then we do subcalls. If S is more than 10K, we add minimum cut of size at most K plus 1 for every pair PQ. It increases allows, but so bag has become big, but every component outside this bag only sees at most mod S number of vertices. So it is great for our induction. Okay. And this is why we are able to prove that for a graph G of tree width at most K with no click separators, we can obtain a family of at most n square tree decomposition with width of size, bags of size 2 to the power big of K log K, and its intersection with any other thing is order KQ. Okay. So wrapping up. So taking the family of all the bags of all this decomposition among all atoms gives us this isomorphism invariant family of bags with the required properties. Okay. This is FPT. This is enough for designing an FPT algorithm. Okay. With doubly exponential dependence on K. And we look through all permutation of each bag, and bags are of single exponential size. But we need lots of more technical ideas to get it down to K power 5 log K. Not much, but we still need to do a lot of hard work. And later, 2015, Elberfeld and Schweizberg gave a canonical decomposition into atoms. And using this, we can derive some sort of isomorphism invariant sort of decomposition of the graph. But still, it is sort of, yeah. So now let me go back to my story. I told you a technical thing. So what I mean by graph isomorphism in graph classes. So what was known, bounded genus, so like n to the power f of g, bounded degree, n to the power f of delta, okay? And fixed minor, n to the power f of h, fixed topological minor, n to the power f of h. So like these are XP algorithm, right? And after Bavai's algorithm came, people have worked on each of these graph classes and obtained following kind of algorithm. Okay, so for bounded degree, people got n polylog delta. So notice that this is a generalization of Bavai's algorithm because delta can at most be n. Okay, for tree width, people got n to the power polylog K algorithm. It's not FPT, but people did get polylog K algorithm. It is still a generalization of Bavai's algorithm because K can be at most n. Graph excluding a fixed minor, n to the power polylog in H, and similarly for topological minor in 2022, they have got. These all algorithms are generalization of Bavai's algorithm because H is upper bounded by n, K is upper bounded by n, delta is upper bounded by n. So not only did they need the full power of Bavai's algorithm, they also need to combine this with the structured theorems, which is known for these graph classes. Okay. So having said that, but for bounded genus graph, there was an FPT algorithm by Kabarwashi, and then Newman got, again, using Bavai's idea, he got 2 to the power big of G log G poly n algorithm. Okay, so it is So this faster FPT algorithm for parameterized by tree width is again uses not only the structure theorem that we proved, but it also uses lots of Babai's idea to speed up this algorithm. So they are able to get tk polylog 1 times k algorithm. So this is a state of art. So now people have been able to mix Babai's algorithm to all these things and able to get some amazing algorithms. Okay, so in this talk, I told you about f of k poly n for graphs of tree with k. Okay, so there are some very basic open questions, right? Is this FPT parameterized by delta, like f of d delta poly n algorithm for maximum degree? Is it possible to get f of h n to the power c for h minor free graphs? Or is it possible to get f of h poly n for h topological minor free graphs? So these were the open questions up until now. And very recently, we managed to show that at least for h minor free graph, the problem is FPT. So, but that requires everything what I told you in this talk and many more ways, many more things. Yeah, it's like a lot of topology because you have to understand how embeddings works, how to compute an isomorphism way of computing this h minor free graph. So it requires many of these tools. So we still don't use algebras, but this f of h is horrible. Like, I mean, I don't even know what this f of h is, but there is some f of h which works. I hope that now that it is known to be FPT, people who know algebra and this group theory based algorithm will be able to design much faster algorithm. So in this talk, I didn't talk about parameterization via elimination distance, feedback vertexes, rank width, and several other parameters. So, and if you really want, there are some very good recent surveys about some of these by Grohe and Daniel Nguyen, one in communication of ASM and other in BCC 2021. So you could have a look at those recent surveys, and it will tell you how much more has happened post Babai's algorithm on these topics. And people have obtained some amazing algorithm mixing structure as well as algebra. So that's all that I want to tell you. So thanks for your attention, and you all are invited to this field of graph isomorphism. Thank you.
Thanks. Thanks, Saket. Thank you. Yeah. So are there any questions for Saket? I think we had a lot of questions already. Anyone has a question or comment? Is there anything in the chat? No, I don't see anything. Yeah.
Just one question.
Yes.
In all these things, the degree sequence does not seem to play any role at all, is it?
Not actually.
Not. I see.
But since if they're isomorphic, their degree sequence will be the same.
Correct. That's right. They should be sort of. So I see.
But there is like the Weisman, Lehman, they use some of these things, but in a very interesting way. So which I don't know much.
Right. Thank you.
Yeah. Any more questions? So then let's thank Saket for Saket.
Thanks, Saket.
Thank you.
Thank you. Wait. So I can see people clapping for you. Okay, Saket.
Okay.
Thank you.
Thank you
So much. Thank you.
Bye, everyone. See you tomorrow.
See you tomorrow.
Yeah. Bye.